Hello, and welcome to Capacitor Time for Physics. Ugh, ugh, oh, that was a little hot. Oh gosh. Okay. All right. It's time for capacitors. Whew. Did you know such a thing existed? Nice. Good stuff. We are going to deal with capacitors today. Remember, a capacitor is two parallel plates. And hey, where's my thing? Okay, and so one of which we're going to charge positively, and one of which we're going to charge negatively from our battery over here. And as far as physical capacitance goes, we have an equation that says my capacitance is bigger when I have a bigger area. It's smaller when my distance gets bigger. So if I get them close together, I can put more charge on there and they'll attract each other more. And capacitors basically store charge. So I put a bunch of pluses here, I put a bunch of minuses there, and they attract each other, so I can disconnect them from the battery, and they will attract each other and just stay there. And then I could charge it up a whole bunch and then put across a really small light bulb over here, and then that's a flash. And so there's a bunch of different reasons why I would want to store charge, and we'll go over that in a bit. The other thing to know is, here's some of the reasons. Photo flash, defibrillators, televisions have capacitors, keyboards are capacitors, like pushing down on the keyboards is a capacitor. You're changing the distance and then it can recognize that. So that's how your keyboard works. And your calculator for that matter. The buttons on your calculator are two plates of a capacitor. When you push them together, the capacitance changes. They have a sensor that tells it when it's down a certain amount. That's how you get a 4 or a 5 on there. And it turns out that if you take a dielectric, some kind of substance, and put it in between the two plates, you can store more charge on there also. And so on this formula here, there's actually a K that you can put at the front of it. That is a dielectric constant that will multiply in to give you a larger capacitance if you put some kind of insulator in there so that you can put more charge on both plates without it arcing across. Between the plates of a parallel capacitor, you get a constant E field. So in between the two plates, all the way up and down here, you have the same E field all the way across it. Outside the plates, out here we get no electric field. And so that's very valuable because then it won't interfere with other parts of your circuit. And if you show that with iron filings, you can see that really it's constant in here. You get a little bit of an edge effect over here where it goes around a little corner right there. So occasionally they'll have a problem where they say, that it changes a tiny bit when you get to the edge. But really, for all intents and purposes, you can say that it's constant electric field in between there. And that electric field is the voltage between the two plates divided by the distance. So aside from the physical capacitance formula, we have another formula that talks about what capacitance actually measures. That value, C, is a proportionality that tells you how much charge per voltage you put on there you're going to be able to store. And so if you attach your capacitor with a battery and you close the switch, whatever voltage you have here, say like 5 volts, since there's nothing else in the circuit, it's going to all go across my capacitor right there, and you can put that in for the voltage down there. So if you know your capacitance is like 1 farad, which is a giant capacitor, you can say that if you put 5 volts across it, it'll be able to hold 5 coulombs of charge. So it's a ratio of how much charge you can store per voltage. And this equation that you do here is used in circuit analysis in place of the V equals IR that we use for resistors. So remember, like in circuit analysis, we find all the resistances down to 1, they work our way backwards with V equals IR. When you do capacitors, you're going to add capacitors to get an equivalent capacitor also. Then when you're working your way backwards through the pictures, you use C equals Q over V, because there's no actual current, at least in steady state capacitor when it's all the way charged. And so you use C equals Q over V for those circuit calculations. Now that we know Gauss's law, we can actually calculate our capacitance, physical capacitance formula. by making a surface that just encloses one of the two plates of a capacitor. So this upper plate with a plus on it is enclosed by a big sort of square thing that just does that particular side with just the pluses in it. You can say that surface integral of E dot dA is equal to whatever Q is enclosed divided by E sub aught. And if you do that, then you get, you know, and your, you know, the electric field on the inside here is constant. You know you're only going to get one area, not the top, just the bottom is going to have an electric field, and it's going to be a constant value. So you can take it out of the integral, and so you get EA. You can take your E sub aught and move it to the other side, and your charge that you're going to get is E sub aught times whatever electric field is on the inside times the area of your plate. Now, since C is Q over V, and we can say that the voltage is the integral of the electric field. You know, the voltage is essentially E times D. And so I can plug into the C equals Q over V, ED on the bottom, and E sub aught A times E on the top, and my E's cancel. So whatever the electric field is, doesn't matter. I get that my capacitance is E sub aught A over D. And so we're able to use Gauss's law in some circumstances that are kind of new to figure out some equations that we already know, essentially. But it's also a way of proving that out here, I have no electric field, because if I'm boxing something there, there's no charge in it. There's no charge in it, I get no electric field. And so that's how I can prove that electric field is 0 out here, and it's really big on the inside there. Here are some examples of some capacitors. Like this is like your classic capacitor. It's a can, and essentially it's two long areas, and then you roll them up into a can. That's why they always have that kind of that shape. And when we draw them as two plates, because essentially if you unroll them, that's what you would get. These capacitors here have two circles like this, and then another circle behind it, and then they encase the whole thing in insulator, so it doesn't touch anything else. And this right here is what's inside a variable switch. You know, a variable switch, you can change how much voltage, how much current can go through it. And essentially you have two areas that when it's off, you have no overlap, and so you get no capacitor. And then you swivel this top bit a little bit over, so it looks like this, and then that little A is the overlap. And since you have a different amount of overlap, you're going to get a different capacitance. When they're all the way over, it's all the way overlapping, and so you get a lot of capacitance. And you just have something that uses that capacitance as a pass-through for the current that's going to happen in your circuit. On a keyboard, you can see that the two plates are attached, one of the plates is attached to the top key, and so you push this down, these two plates get closer together, then you have a detector that detects when the capacitance gets beyond a certain amount, and then it puts a current through it and says, draw K. Because we know that we can use Gauss's law to find the capacitance of parallel plate capacitors, it turns out that there's a lot of other different types of capacitors that we now can calculate because we can use Gauss's law on them. The first one we're going to talk about is a cylindrical capacitor. On a cylindrical capacitor, I put all my positive charge in the middle, and I put my negative charge all the way around the outside. And so the two plates aren't the same size, and so that changes the dynamic a tiny bit. But when we use our Gauss's law, our surface is going to be in between the two casings. And so like if that's the interior one and that's the exterior one, our surface is going to go in between the two of them. And so the charge that it's going to enclose, and it's going to be a cylinder, right, like that, and it's going to enclose the inside part of it. And so what I get then is that the surface integral of EDA equals Q enclosed divided by E sub aught. My electric field is going to be constant because I'm the same distance away from the charge, and so I can take it out, and I get that the Q is equal to E sub aught E over A. The difference this time is that I'm actually going to put the area in because I want to actually find what the area is. So it's 2 pi r times the length. That's going to be the area of a cylinder, and just the part that's around the circular part, because the end caps are going to cancel out to 0. And when I do that, I get that the electric field is Q divided by 2 pi r L, because I just divide by that area. And I take that electric field and I integrate that to find the potential. And you know, I have the R, and the length is a constant, so I take all the constants out, and then I take the integral of dr over r. Now unfortunately that's my x to negative 1, that's really hard power rule wise, But if you just know, and you have to kind of memorize this, and hopefully you've gotten to this part in calculus, I know the BCers have, to know that the integral of 1 over r is the natural log of r. And since in this case I'm doing it from A to B to go find the capacitance all the way from the interior radius to the exterior radius, I'm going to get the natural log of A minus B, and with natural logs, minus is the same thing as divided by, so this is what I get for my voltage. It's Q divided by 2 pi e sub naught L natural log B over A. If that natural log stuff is confusing you a bit, we'll talk about it in class, but it's really not that hard. It's just another one of those kind of rules for integration that you have to memorize, that 1 over x, or in this case r, and you integrate that, you get the natural log, and then you have some kind of rules for using natural logs with multiplication and division. Then I have to use the same equation. So remember, with capacitance, I always use Gauss's law to find the Q. I use Gauss's law to find the V, and then I'm going to find capacitance by taking Q divided by V. So I take this, which is my Q I got was this. So Q is this. And then I divide it by V, it's this. Oh, no, sorry. This is my Q. And then this part down here is my V, and then my Q's cancel, and I take this and put it on the upper part, and I get 2 pi e sub naught L over natural log over B of B over A. Yeah, I kind of wrote all over this. Go back in the video and see what it actually looks like, but I'll be writing on it. But essentially, you can always find the capacitance of anything that you can do a Gaussian surface on. So if it's a nice, even electric field, you can find the capacitance. Now, the nice thing about this one is it allows us to do shielded cabling. So if you ever notice those cables that like have a center to them and then they have a conductor on the outside also, the reason they do that is because if you do that, all the electric field made by those two is contained inside the wire. And so this kind of wire makes no electric field on the outside, just like in a parallel plate capacitor, you get nothing on the outside. So this kind of wiring does not affect other wires that are happening around it. And so your more expensive cables, your iPhone cable, is done this way. It makes it harder for us if we're doing a house project because we have to kind of cut this and then strip away a little bit of it and attach this to our positive and negative if we're going to use it. But if I have a normal wire which has 2 wires next to each other, these are, and I have current going this way and that way, these shoot off magnetic fields all around them in this direction and this direction. What that does is any other wires that are out there will work better or less well depending on which direction they're going. And so it can affect other things. And so if you're dealing with really high voltage especially, you want to use this kind of cable so that you don't get any interference between your cables. You guessed it, another capacitor. This time a spherical capacitor. If we have 2 things, we put the positive on the interior circle and then we put a sphere of conductor on the outside where we put our negatives, we can use that as a capacitor also because, again, just like every capacitor, the pluses and the minuses will attract each other, and so if you charge them up and then leave them alone, they just hold that charge. And we can find out what the capacitance of that sort of capacitor is, same way we've done for all the other ones. We start with Gauss's law. This time our area is 4 pi r squared, so we get our electric field, we get this equation, and remember we're going to solve that for Q eventually. Actually, I don't think we need to in this one, but we use that electric field, we take the integral of that from B to A, the inside radius to the outside radius. All our constants come out, and we just end up with dr over r squared this time instead of just r, which is easier for us because we can make that r to the -1. We get our integral right there, and on this one, we end up doing a common denominator there to get, you get b minus a over ab for this bit. But then when you take the capacitance, you take the capacitance is Q divided by Q over 4 pi e sub naught times that bit. The Q's cancel, and essentially you flip this to the top. So what you get is the inverse. which is this. Once we get that formula for a spherical capacitor, we can make it for a special case where we only have the inside. And we're going to say the outside is infinitely far away, way over here, but actually even farther. And essentially all that does is we take our regular equation for a spherical capacitor and we set B equal to infinity. And if we use this little thing right here, it'll make it easier for us to do that. If you multiply by 1 over b on both sides, that's basically multiplying by 1, and we get this equation here. When we do that, we can see that if b goes to infinity, that all will go to 0. And so you end up just with 4 pi e sub a, and a we've called as the radius of the inside, which we just say is r. So the capacitance of just a sphere of charge sitting there is 4 pi e sub times whatever the radius of that sphere is. I would like to read you some of the reviews for our extreme snack today. First one says, absolutely destroys your mouth. Very sour and delicious. Will buy again once my mouth gets out of therapy and has a full recovery. Despite the warnings on the label, I ate a bunch of them at once and it was well worth it. Don't do that. If you have a cut, burn, or any other damage on your tongue or cheeks prior to eating the sour balls, it is highly recommended that you do not eat them. Or that you not eat them at all. That's really up to you. I personally will not eat many of these, but I do buy them for an occasional treat. Yeah, here's one. Only eat one at a time and make sure not to leave them in one spot for too long or it will not be pretty. What does that mean? Okay, I'm not doing that. These are not a joke. They will make your tongue raw if you're not careful. Only eat one at a time and do not leave them in a... I don't like sour things. But we have them. They came actually all the way from France. Par avion. They're fragile, apparently. Yeah, why am I getting sour candy from France? I don't know. Here they are. I'm about to put one in my mouth. I may be sorry. They look pretty innocent, but I'm thinking they're going to be death. So I'm not supposed to let it be in one place too long. Okay, here we go. Oh, that's not just sour, it's nasty. Oh, here comes thousands of saliva. Oh, ouch, ow, oh my goodness, it hurts your tongue. Move around. Okay, all right. Who did this? France! That's just not pleasant. Okay, that's starting to wear off. Holy crap. It just tastes bad. All right, I'm going to the candy part, but even the candy's not that great. Wow. It was kind of chemically and sour and bitterish, kind of like. Honestly, don't know if I'd recommend this one, but there are a few. Well, I can try when you get to class. I'll try to get some durian too for you. We'll see if I can find it. I want to see if I can get the durian. It's actually ripe, not in the big spiky thing, because that didn't work out last time. Anyway, sour. Apparently there's a video of somebody putting a bunch of these in their mouth on YouTube. Ask Chris about it. This is his fault. Whew. Let's take a break from that hard calculus stuff and do some review of just combining capacitors. And it turns out that if you remember the equations for adding resistors, the capacitor ones are just the opposite. And it's based on this physical capacitance equation. Essentially, when I put them in parallel, I'm making the area bigger. So if you look at these two plates, essentially I have double the area there. And the area is on the top of my capacitance formula. So that means that when I make the area bigger, it should make my capacitance larger. And so when I add capacitors in parallel, I just add them. So if I have 5 farads and 10 farads, I get 15 farads for the whole thing when I add them in parallel. When I add them in series, it turns out they have to share their Qs between the two different plates, and so that makes the capacitance less. And it ends up being exactly the same equation that I used to make it less in resistors. I add their inverses. So if I have 2 farads there and 2 farads there, I'd go 1 over 2 plus 1 over 2 equals 1 over capacitance total. That's 1. The inverse of 1 is 1, so my total capacitance would be 1 farad. You've done that a lot for resistors, so just realize it's the opposite equation. Your turn. Take this one and do some circuit analysis on it. So you're going to go to the most complicated part up here first, so you do those two in parallel. You're going to draw a picture that has one capacitor for those two. Those will be in series, and then you add those and get one capacitor. Do C equals Q over V with this voltage and this C to find the Q at this one. Then go back a picture. When you go back to a picture that's in series, Q is constant. When you go back from this one to those two, which are in parallel, then V is constant. Use that to find the equivalent capacitance for the whole thing, and then go back and find the Q on C2, which is this one. So go all the way down. Once you get the equivalent capacitance, that's the first question. Go backwards through all your pictures and find the Q there, and you have the answer for that. So do it. Don't look at the next slide until you're done. So when you do these two up here first, those are in parallel, so you just add them. So 2 and 4 gives me 6 microfarads. And I should probably redraw them, but it's pretty easy, so I'm not going to this time. Don't tell anybody. But I get 6 microfarads for those two. Then I get 3 here, and I have to add their inverses. So 1 over 6 plus 1 over 3, 1 over that, and I get 2 microfarads as my answer for the whole thing. And then if I want to find out what the charge on C, oh, sorry, it says C1. I couldn't see that. It said C2 before. For C1, charge is what's going to be the same for all of them. And so I use this and that to find the charge of 24 microcoulombs for the whole thing. And then that's going to be the same for the 6 microfarad and the 3. And so that's what I'm doing here with 3 and 6. I get 8 volts across that top bit over here. I get 4 volts for across this bit. And then all I have to do is take this 8 volts and throw it into this right here to find is it C, oh, it's C times, so my C is 4 microfarads, and I have 4 there, so I get 16 microcoulombs. I did it again. I found C2 again. I actually was trying to find C1. So actually for C1, it is 2 times 4, or 8 microcoulombs. That's my answer for this one. 8 microcoulombs, 60 microcoulombs. I can also use calculus to derive all those energies stored in a capacitor formulas. I know that I get a direct relationship between V and Q. That's just my C equals Q over V formula. And because it's a nice, easy relationship, I take the area underneath that, and I can find the work because I know that W equals V times Q, because U equals QV. That was my formula for energies. So to find the change in energies, which is work, I find that energy in 2 different places. So it's the integral of V dQ. When I do that, I get this nice equation, and I put C equals Q over V, and I can also get that one. Really, you just memorize those formulas, but know that they come from a bunch of calculus. Dielectric seems like the easiest part of capacitors. Essentially, you just add an extra K in your normal equation. So instead of E sub A over D, you get K E sub A over D. So you just multiply whatever constant you put in between the 2 plates, but it adds a couple wrinkles. APC likes to charge up a capacitor and then shove a dielectric in there and see how that changes the circuit. And if you do that with the battery still attached, it changes, as opposed to if you do that and you disconnect the battery. So the first thing we're going to do is say, okay, if we leave the battery connected, this side over here, then the battery is going to keep the voltage constant there. And so that 10 volts will not change on the connected side. The capacitance starts at 5 microfarads. It's going to change to 10 microfarads when I throw a dielectric of 2 in there. And essentially, when I do that, the voltage stays constant and I find a new Q. However, if I disconnect the battery, no more battery, what's going to stay constant is whatever Q I had at the beginning. And so with my 10 and my 5, I would have had 50 microcoulombs across this capacitor. With no battery attached, that stays constant. I still get the 10 microfarads when I throw the dielectric in there, but now when I do it, I get a voltage of 5 volts between the two plates. That wouldn't have happened if it was connected because the battery would change it to make sure it's 10. And so there's two different ways of doing it for even if there's just one simple capacitor in a circuit. But when I put 2 in parallel, so if I put my 2.5 microfarad capacitors in parallel with my same 10 volt power source, and then I end up doing my 2 dielectric on just one of the capacitors, it's not so bad if it stays connected, because if it stays connected, I'm still going to get 10 volts across each of them. I can do my circuit analysis with the 10 volts, the 2.5 microfarads on that one, and the 5 microfarads for the bottom one, and I can see that that one has 25 microcoulombs, that one has 50 microcoulombs. It gets more complicated for the one where I disconnect. So if I take this and disconnect it, the 50 microcoulombs that I had on both of these, because to start with I had 25 microcoulombs on each, that charge is free to move from one capacitor to the other on either side. And so it doesn't have to stay the same for each capacitor, it has to stay the same for both capacitors together. And so the thing that is the same for each capacitor is the voltage, because if I'm attached by a wire with no resistance, the potential for each side has to be the same. So V1 equals V2, and then I can use my C equals Q over V and solve for V and say that the charge on 1 divided by the capacitance of 1 has to be equal to the charge on 2 divided by the capacitance on 2. Now my capacitors, as you know, go to 2.5 and 5, the 5 because I'm putting the K of 2 in there. On the tops, I know the total of my charge has to be 50. And so I have an equation that basically says Q1 plus Q2 equals 50. So I plug in Q1 on one side, I'd say 50 minus Q1 on the other side. Then I can cross multiply and solve, and I can find that Q1 is going to have 16.67 microcoulombs, and I can take 50 minus that to find out what's on Q2. I realize that's fast. You can go back and watch the video part again, but we'll talk about that one in class 2. Last bit on dielectrics complicating our lives, because they do complicate our lives a little. We can figure out how much a dielectric changes our capacitance if it's on the entire capacitor. But if I shove a piece of dielectric in that's only 3/4 of the empty space between those, things get a little more complicated. It turns out that what I'm really doing when I do that is I'm going to have 2 different capacitors. One that's the top bit with a different distance and our initial E sub naught A over D, and then 3/4 of my distance I'm going to use for another capacitor down below it. But those 2, which like essentially I'm going to do this, are in series. Now this distance is only 1/4 of the distance, and I use E sub naught A over D. This one is 3/4 of my original distance, and I use the dielectric on there too, so I have K E sub naught A over D. Now since these are in series, I add their inverses. So these are the 2 capacitances I get when I use 1/4 of the distance and just E sub naught A over D, and the 3/4 of the distance and the dielectric in there as well, and then I have to add them as inverses to get a total capacitance. So that's if I shove it in and it's like 3/4 but all the way across. I can also shove it in so it's only half of the distance. When I do it that way, I'm adding them in parallel instead. And so the total 22 that I got up there, I'd have half of it 11, so that part doesn't change. The other half would be 11, but I shove a dielectric of 2 in there, so I get 22. But since those 2 are in parallel, I just add them, I get 33 picofarads for shoving it in that way. Notice both ways, either shoving it in all the way across, which gives me a series, or in parallel will give me a higher capacitance than my original capacitance that I got. And again, now it's kind of complicated, so we'll talk about it in class, but it's not too bad, and it's based on circuit analysis of capacitors, which we've done before, so it's not some new Gaussian weird use for capacitors, which the first part of this was. Capacitors, they are your friend. I'm not a big bad wolf. I'm a fox, but I still howl. Roar! Do your physics, or I come for you.